In this video we'll be discussing buffer solutions, and it's all about controlling the pH. A buffer solution resists changes in pH when small amounts of acid or alkali are added. They are made from a weak acid and its respective salt, or a weak base and its respective salt. So if we were to have a basic reaction of a weak acid in solution, we have our acid HA with water, and that is in equilibrium with acid anions and H3O+. The equilibrium will be over to the left since it is a weak acid. Now, if we were to add the salt of the acid to this solution, we are effectively adding just more acid anion, because the salt breaks down into its ions, so we get more A-. So this results in a solution that has a lot of acid, RHA, a lot of acid anion, A-, and a lot of H3O+ ions, and this makes it acidic. This is when the magic of buffer solutions happen. If we were to get a small amount of an acidic substance and add it to our solution, the extra H3O+ ions will lower the pH. The solution doesn't want to do that. Through Le Chatelier's principle, we know it will want to minimize the change. So the A- in the solution will react with the extra H3O+ to move the equilibrium back over to the left to minimize the pH change. Whereas if we were to add a small amount of alkali, we'll get OH- put in, and this will react with the H3O+, which will increase the pH. Therefore, our acid, the HA, will react with H2O to make more H3O+, pushing the equilibrium over to the right in order to make more H3O+, to lower the pH. The main thing to remember here is that our acid will provide H3O+, and our salt will act as a sink for the H3O+ added. To kind of test your understanding, go do the same but with a basic solution. Figure out what would occur if you were to add a small amount of acid to the solution and then a small amount of alkali. If it helps, put in real chemicals like ammonia and ammonium chloride. In the exam, you are likely to encounter calculations involving buffer solutions, and we can simply use the equilibrium equation to go about it. Unlike previous equations with weak acids, with buffers we can't assume that the number of protons equal the number of anions, since we added in a salt that provided extra anions. However, what we do assume is that all of the acid anion in the solution is equal to the concentration of the salt added. This is because the salt added provides almost all of the anions, so it's a safe assumption to make. So with an example question, we need to try and calculate the pH using 0.2 moles per decimeter cubed of ethanoic acid and 0.3 of sodium ethanoate. This is the salt. And we can go about it by rearranging our equation to have Ka divided by the salt over the acid. This will give us the concentration of the protons. And this is equal to 1.16 times 10 to the minus 5. And to get to the pH, we just use the minus log formula to get 4.94. And that is the buffer pH questions. They could, however, ask you to do it the other way round. So how much acid and salt do we need to have a buffer with a pH of 3.50? Well, first we're going to want the concentration of the H+ ions, so that's 10 to the negative 3.50, and with the Ka of ethanoic acid we divide it by the H+ ions, and this will get a ratio between the acid anion and our acid. So for every 1 moles per decimeter cubed of ethanoic acid, we're going to need 0.055 moles per decimeter cubed of sodium ethanoate to get a buffer solution of pH 3.5. So it's just as easy to do it the other way around. There is one main equation to take away from this, and it is the Henderson-Hasselbalch equation. It is our Ka equation, just rearranged and with the minus log taken from both sides, and it results in this, which is a quicker way to solve the buffer questions because you didn't have to keep converting the pH. And that is all with buffers. I hope you enjoyed the video. Until next time.